Welcome to Past Summit and to my session on improving analytic performance with Columnstore indexes. This is a fun topic. I love it. It's brought me great deal of use in my career, in helping others, in working with large amounts of data. So it's a fun topic. I enjoy it. Making things faster has kind of always been a passion of mine. So if it is for you as well, and for managing giant mountains of data, hopefully you'll enjoy this as well. So I'm Edward Pollack, but first off, before I talk about myself and jump in, here's everything that PASS has to offer. PASS is a big organization. PASS Summit is one piece of it. There are also many SQL Saturdays out there, which are all-day Saturday events that talk about all kinds of sessions just like this, and talk about all different areas of data, professional development, and so on. I run the one in Albany, New York. It's pretty awesome. There's also PASS Marathon. There's virtual groups. You can volunteer and get involved. There's local groups. There's tons and tons. So if you haven't checked out everything PASS has, check it out because there's a lot and it's pretty much free, and free is a great price. Also important are session evaluations. Please submit an evaluation, evaluate me, evaluate my session, evaluate the content, evaluate the format, evaluate everything, because evaluations help everyone get better. It helps me get better, it helps PASS get better, helps the conference get better, it helps everyone. So please submit session evaluations. This is a little bit about me. I'm a senior DBA over at Datto in Albany, New York. I live with my family. They keep me on my toes. I trip on Legos all day. I've published some books. I've written a lot of articles. I've spoken at a lot of events. So I've been doing this for a while, and I like it a lot. But you're not here to hear about me. No one really cares too much about that. What you care about is giant mountains of OLAP data. And that's what we're here to talk about. So here's the agenda. We're going to quickly review OLAP data storage and what you can do with your OLAP data. OLAP is online analytic processing. That's big reporting analytics style data. We're going to introduce Columnstore indexes quickly. We're going to talk about guidelines, best practices, and ultimately how to make them really, really fast, because you can just plop them in place and they'll be good, or you can optimize them and they won't just be better. They'll be like orders of magnitude better. And so there's a huge difference there, and that difference matters, and we'll talk about it. We're going to talk about maintenance briefly, because maintenance matters on anything we're going to build. How do you maintain it? And then other options. What are the other things we could possibly think of to do with Columnstore indexes that might be good ideas, or might just be plain old silly? Whichever it is, though, we'll talk about it, and then we'll wrap up. All right. So first off, we have a choice. Where do we put OLAP data? We have more choices today than ever in the history of mankind on planet Earth ever. Like, people have been here forever, and we have many, many choices. And where we put it matters. It'll affect how we use it and how we access it and how fast it is, and does it meet our needs. So you could put piles of data environment, like structured data lakes, where basically, excuse me, did my screen freeze?
Yes, Ed. Sorry.
Oh,
Yes, for
I don't
everyone
know
over
why.
there, for everyone
Okay.
in the audience. Sorry for that, but hey, this is the virtual world that we live in. Back to you, Ed.
Okay, thank you. I did not see that, but if it happens again, I will keep an eye out for you. Thank you. So where do we put our data? Unstructured is great because if you don't really know what you're looking for or how you want to present your data, it's probably good to just dive into it and have fun. The downside is it may not necessarily perform well when you begin having a better idea of what it is you want and where you want to put it. Data warehouses are great places for analytic data. Things like analysis services is the Microsoft implementation. There's Redshift. There's many others out there too that provide a place to put warehousing data. Data warehouses are great, but they're also a new product you have to learn. They involve their own languages, their own access tools, their own everything. So you may or may not want to buy into that, depending on what you're familiar with and depending on what your organization wants to do. There's third-party analytics software. This stuff is great if you want to be hands-off and not be involved in maintaining your data. The downside is you're giving somebody else all your data, which may or may not be what you want, and your data won't be alongside the source data, which you might care about as well. So up and down sides to everything, including all 5 of these options. Traditionally, many people used to put reporting data into transactional tables. This is fine until it gets big, and then it becomes slow because it's not built for that. So OLTP tables, just classic clustered indexes, non-clustered indexes, are great for small dimension tables, small lookup tables, small log tables. But once you're talking, billions of rows, it doesn't really scale very well. And honestly, it doesn't really function the way you want it to. So what that leaves us with, the option we're going to really discuss today, is we can store data in a relational database in tables optimized for analytic data. The primary benefits of this is it's in a familiar place, It's probably kind of close to your source data, so you can transfer data between source and destination quickly, and you can update it and you have full control over it and do whatever you want with it. Schema-wise, data-wise, you're in control. It can be on your hardware, it can be in the cloud, it doesn't really matter where it goes. It can be on a managed instance, totally up to you. You can put analytic data anywhere. So this is kind of just an overview of the many options that are out there. This is one of them. I like it a lot for its convenience and cost. So what is a Columnstore index? Basically, it's built for analytic data, and that's its sole purpose. It can be used for other purposes, and it can provide some benefits, but its purpose, its primary reason for existing, is analytic data. It's a highly compressed data structure. It's built for large data sets. When I say large, I mean at least millions or billions of rows. If you're talking about a table with 1,000 rows in it, it doesn't really help you at all. We're talking large data. The larger, the better. And we always exaggerate our speed gains, but there's no exaggerations here. Using this kind of index, you can shrink an index to a tenth, a 50th of the size it originally was, and you can make the speeds 10 to 100 times faster for real. And we'll talk about how that happens later and why. And I'll emphasize the fact that I'm not being sarcastic or exaggerating. You can get some really amazing gains off of Columnstore indexes. Behind the scenes, the technology in this stuff is not unknown. It's not new. It's been around for a while. Much of what makes analytic data fast in analysis services, Power BI, Power Pivot, and a similar technology that's used in other services or providers out there that will compress and manage your analytic data. It's the same stuff basically behind the scenes, very similar. And so we know it works, and we know it works in different environments, and it works especially well here. The key behind that, though, is it's not just another index. When you use a Columnstore index, you're not just slapping an index onto your table. You're fundamentally changing how the data is stored to make it really efficient for an analytics. All right. So with that out of the way, a key to speed, we're going to talk about why is it fast, how does it work, and then how to get the most out of it. That's kind of our progression here. So first off are the keys to speed. What makes Columnstore indexes fast? Number one is compression. Columnstore indexes aren't just compressed, they're compressed really, really well. And the reason why they compress well is that you're not compressing a row of data. We have 100 columns that are all different looking. You're compressing by a column, and the column has the same data type and very similar data within it. And therefore, it compresses really, really well. Your compression ratios will be 20 to 1 or better very, very easily. And the benefit of the compression ultimately is that your data remains compressed until needed. So it's compressed in your storage system. And when you begin reading and writing queries and accessing it, it stays compressed into the cache and is not decompressed until you actually need it for a query. And so because it stays compressed, you're saving storage, you're saving memory. And that by default makes things much, much faster. You're moving less stuff around over your storage, over the network, over through memory, through everything. So compression is huge. We can talk quickly about compression. I like demos. Live demos are fun. They're exciting, especially when they break. So we're going to be basically working with our own data structures today. I'm using worldwide importers, but this is basically our own data structures that I built already. So any create tables, any create indexes you see here, I've already done it all because you do not want to sit and wait while I build a giant table in a live presentation. That's boring and nobody wants to see that. So we're creating a table here based off an order table, and it's the classic transactional table. I insert a mountain of data into it. I create an index on it, a covering sort of index in the date column because we often search by date. And just for information's purpose, we'll take a look and see what's in there. This took a little while to get a count out of the table, but there we go. There's about 23 million rows in this table. And we can see it took a whole mountain of reads to get that data, like 50,000 reads to get the data. And there's an execution plan that shows an index scan because I counted every row in the table, and it literally did that. All right. So what can we do? We can create a table with a Columnstore index instead and show what does this look like ultimately. So create our Columnstore index table, insert a mountain of data. This is the command to create a Columnstore index, create a clustered Columnstore index. So we're going to be using clustered for most of the session. It makes a lot of sense. And then we can look at the data and see how much we have here. You can see same amount of data. Ran a lot faster though because we're using a Columnstore index now. And we can note that it did a lot less reads than before. We'll talk more about performance later. Last but not least, though, I want to compare the storage difference between the two. So I have a quick query here that I wrote that'll just basically take the space used for a few tables, throw it into a temp table, and then read it back. The details don't really matter. Really, the results are all that matters here. So we run this. I'm actually going to turn off the execution plan for this and then run it. It'll be faster. There we go. save time, do things faster. It's better that way. So we'll run this, we get our results, and we can note that the original table we created, OLTP, is about 5 gigs, about 0.2 kilobytes per row. The Columnstore index table is 340 megs total, about 0.015 kilobytes per row. That's a big difference, less than a tenth of the size, about a 15th of the original size. Without any additional work, I just threw a Columnstore index on the table, and it shrunk that much. So that's a big deal. So far, we can see that the compression has a big impact. So let's move on. What else makes Columnstore indexes fast? Another one is metadata. So unlike statistics on tables normally, which get out of date and they're not necessarily accurate in their estimates, we store metadata in line with our compressed data, and that metadata is accurate, 100% accurate. And so it includes mins and maxes and counts and things that will help us figure out how to execute a query very quickly. Because if we know the min and max on a group of data, and I'm asking for something not in that min and max, well, we can ignore it. Done. And so metadata helps SQL Server not have to read through mountains of data. It can actually skip a lot of data and ultimately get to the data it needs only and not the rest. So the metadata stored in line with the compressed column store structures makes it very, very fast because we can skip a lot of reading and move through the metadata instead. Next, batch execution. This is a newish thing in SQL Server, but not so newish anymore. SQL Server, normally, when you're running through execution plans and doing row-based work, is a row-by-row behind-the-scenes effort. And so as the queries are processing, row by row by row, which in a transactional environment often makes sense because you're operating on small row counts. But in this world, we're operating on large row counts, massive row counts. So row by row is kind of slow. And by being able to execute and operate on a batch of rows instead of one by one by one by one, everything goes a little faster. Execution plans can move quicker because you don't have to pass back and forth to move rows through the execution plan. So in general, this makes things much, much faster. I'm not going to go into the details of batch execution. We don't really have time, and it's not fully relevant to this presentation, but I will at least show how you can tell the difference between batch and non-batch execution. So we can look here at, I see potential for questions coming up here. So I'm going to pause for a moment and let Eric jump in.
Hey, thank you. So we got a question. Well, one is a comment. They're mentioning that your screen's a little bit too small for SSMS. So that's just a comment, but we do have a question. What is your take in using column store indexes exclusively on low selectivity and or non-selectivity columns? Thank you, Christian, for that question.
Good question. I would say, and we're going to talk about this in a little bit and bring a lot of clarity to this, but I would say the column store index, the optimal use case for it is where you can order your data in such a way that you can benefit from being able to eliminate values you don't need. So if your data is all ordered by a column, it doesn't matter if it's selective or not, but if it's ordered, that will help get the most out of your column store index. And I don't want to jump ahead because I'm going to talk a lot about this soon. So I think the answer to that will come soon, and I don't want to spend a lot of time trying to jump ahead to things we haven't talked about yet. So I think the answer to that will show itself soon. But if not, feel free to ask more questions and call me on it and give me a hard time because I'll deserve it. I made the screen bigger here. I hope that helps. No one's complained yet, but this is not a problem at all. I don't mind making it big. All of us hard of seeing can now see, and I can see better too. So thank you. Anyway, jumping back to batch execution and how it looks. If I run a query against a transactional table, that's what this one is, I can see I get my results back. It's a subset of one day of data. And I can see in the execution plan that I didn't index seek, which is great. But I'll notice that it's against a row store and it's row execution mode. And so we know by looking at this that this is behind the scenes row by row, and that's how it works. Which again, for transactional tables, it kind of makes sense. And there are ways to use batch execution against transactional tables, but at a high level, it kind of makes sense that this is used on a row store table. If we were to do the same query against our column store index, we get our results back and can check the execution plan, and we'll see that it says the column store index scan and that it was a batch execution. Now, a few notes here. First off, you're going to often see column store index scan as the operator and a column store index. We're often trained to think that index scans are bad. That is not the case here. An index scan against a column store index is perfectly fine. That's the operator you're always going to see. It does not mean you scan the whole table and paid a penalty. It just means it's how it works. Second thing to note is there's a missing index suggestion here. Hey, put index and order date key, and this will be faster. Well, the data that I have right now is not ordered, and we'll talk about that soon. When I threw my data in this table for a test, I did not do anything to order it. I just said, dump the data in however it is, and we'll work with it. So it's an unordered mess. And that's why we're getting index suggestion here. But we're going to work through that later on and fix it and get rid of this. So before you ask why there's a green blob there of text, I'm going to tell you right now we're getting rid of it and making it better. I promise. Cool. Let's jump back. So that's batch execution. Batch execution lets queries run faster by operating on rows in groups rather than one by one. Let's continue. Next key to speed. This is huge for writing data. So typically in an OLAP environment, you don't write data constantly. You write data in data loads that occur once a day, twice a day, once an hour. But on some set schedule where you control the data loading, it's not a million users all jumping in and doing stuff constantly. And because of that, we can actually take great advantage of bulk loading. And so normally bulk loading is something you do with like files and importing BCP of lots of stuff, and you want to minimally log it. For a Columnstore index, this is what you want all the time. So basically, when it can happen, when you have enough rows, data will be inserted using a minimally logged bulk process, which means if I insert a billion rows, you're not going to sit here and wait for the transaction log to log a billion rows. It'll be minimally logged, and that'll make it much, much faster. And in an OLAP environment, this makes sense. You know, no one's ever going to say, hey, you loaded a billion rows. We want to do a point-in-time restore to 5 million rows in. No, you're going to either redo the whole thing or work out from the end, but you're not going to go back to the middle. So minimally logged makes perfect sense. It greatly increases speeds of inserts because you don't have to worry about logging the whole thing anymore. And so for these kinds of workloads, it 100% makes sense. So we've talked about the overview of Columnstore indexes and basically what makes them fast, what makes them awesome. So now we can dive into how they work. And this will help bring a lot of clarity to what I was talking about before, because in some instances I mentioned things that weren't fully explained yet. So now we'll fully explain them. So in a Columnstore index, data is not stored in any way like how it's stored in a rowstore binary tree kind of deal. This is totally different. So what you have are two structures here that maintain your data. You have row groups. A row group is a batch of rows. It contains to 2 to the 20th rows in a batch. 2 to the 20th is, for the sake of argument, about a million rows. The exact number doesn't really matter here. I'll mention it later on, but it's about a million rows. So you have row groups that contain about a million rows apiece. And then you have segments. A segment is an isolated group of data within a row store. It has metadata included in line with it. And a segment is for a column. So if you had a table like this one that has 4 row groups, so maybe 4 million rows, and it has 6 columns, each row group holds about a million rows, and each row group has a separate segment for each column. Each segment is independent from each other segment. This is how data is stored, and the main reason why this is awesome is because each row group and each segment is kind of independent of all the rest of the row groups and segments. So you don't have to read them all together. This is not like in a rowstore table where I have 50 columns and I go to the cluster index and grab all 50 columns when I only want 2. You still read all those pages in memory and the pages of all the columns. So here we don't have to do that anymore, and that's really nice. We can view the metadata in SQL Server very easily. So there are DMVs, dynamic management views, that contain data about our row groups and our segments. This query here will return data about the row groups. And the details, feel free to steal my queries later and use them, adjust them, play with them, whatever. But what we can see here is that in my Columnstore index, I have a total of 27 row groups. It starts at 0. You can see that 26 of them have that maximum number. This is 2 to the 20th rows that have been loaded in. Perfect. They're all compressed. They're all done. No one's going to add any more rows to these ever. And then I have one more row group at the end that has some rows from that last section of the data load. So you can see how many row groups there are in my Columnstore index. In this case, there's 27. You can see the size and the number of rows inside of it. Next, we can view our segments. The segments are also stored in Dynamic Management View. We can jump in and look at it and join it to other views and tables to get other related information. So when we jump in here, we have a lot of information. We can see that for each segment, there's 437 segments in this index that belong to those 27 row groups. And we can see which table, this one, the one I built, what the index is for it, what column the segment belongs to, and some more information about the mins and maxes and counts and things. So you can view some metadata about each segment within your Columnstore index. And that's pretty cool. So let's jump back and talk about more of how this works. So there's 2 things. Hi, Eric. What's going on?
Hi, how are you?
Q&A is beautiful.
Sorry for that. I have a question from Michael. Will the Columnstore index use a partition scheme in your table if your table is partitioned?
Yes, and in fact, partitioning a large Columnstore index is a very good best practice to have. Great call. We're going to talk about that soon. So you've already jumped ahead and graduated. Thank you. That was awesome. But yes, partitioning and Columnstore indexes go great together, and we'll talk about that soon.
And just something very quick before we move forward. How do you deal with tables you need to do update inserts or on frequently?
Great question. I have a whole section of that coming up next as well. In general, the key to that is inserts are good, deletes are not so great, and updates are very bad. And if you can batch it, being able to batch it helps, but you don't have to. And there's actually a structure built into place that helps with that. So I'm going to dive into architecture, answer some
Awesome.
questions, and move on, and we'll be doing good.
Sounds good, Ed.
Thank
Thank
you.
you so much. And thank you everyone for all your questions. Very
I love
realized.
questions. Thank you. So there's two reasons why Columnstore indexes are fast in terms of the bulk of your data. How do you limit your data use? So the first is segment delimitation, because each segment is a column and each column is a segment. Because of that, let's say I have my hypothetical table here with 6 columns and 4 row groups, 4 million rows. Let's say I issue a query just for columns A and B, and that's it. I don't touch C, D, E, and F. What happens is when I read my data into memory to use it, I won't read C, D, E, or F. And so immediately, by just querying 2 columns, I don't touch any data pertaining to, to 2/3 of the table. And so we end up with a structure on the right here that shows 2 segments times 4 row groups, or 8 segments. So we started off with 6 times 4, 24 segments, and down to 8. That's called segment elimination. So when you write a query against a Columnstore index and you do not access every column, all the columns you don't include have been eliminated automatically. You don't have to do anything, they're gone. And so you saved a lot of reads and writes and effort and everything. Writes, no writes, but you saved a whole lot of reads and effort by not having to touch that data. The other side of this is row group elimination. So in addition, that metadata that's stored in each segment tells SQL Server the max and min values for that column in that row group. As a result, if you have a where clause on a column, and we know the mins and maxes, in theory, if the query does not meet a min or a max, it doesn't fall in that range, we can eliminate that row group altogether and ignore it. Very, very often, you're going to order your data by date. And if you're querying for a small date range, let's say, for example, I'm querying for a small date range here over my 2 columns, and that date range is encapsulated solely in one row group. This happens. So now I've taken my 24 segments over 4 row groups and said, you know what? All the data that I need is in the first row group based on my filter. The rest isn't needed. So I can go from 24 segments to 6, from 4 row groups to 1. This generally requires some sort of ordered data, which we'll talk about soon. Of course, the key to success here is combine them. Let's say I queried for a small date range in one row group and just for 2 columns. I want a simple metric over a few columns, and that was it. I go from 24 segments down to 2. Now, as your table gets bigger and bigger, this gets way more dramatic. Like if you want last month's metrics for some revenue database and you have 10 years of data, you've eliminated this massive amount of data automatically by row group elimination. So the last piece of architecture here, which will address what do you deal with constant inserts and updates and deletes? And the answer is the delta store. So originally, when Columnstore indexes were first architected, they were not writable. That was okay for a warehouse that's not loaded very often. You can kind of reproduce the whole thing or do it in chunks or partitions, but it got kind of cumbersome. So the delta store is a separate structure from the Columnstore index. It's a binary tree structure, classic row store kind of index. And what happens is if you perform frequent small operations on your Columnstore index, those operations will hit the delta store first and sit there. The delta store will then accumulate small batches of write operations. When there's enough of them, it'll then asynchronously write into the Columnstore index. And the reason this exists also is because compressing a row group is expensive, but we don't do it very often. We don't write to this thing constantly. So typically, for most common use cases, you don't have to worry about it. But if you have a scenario you're writing the Columnstore index hourly or minutely or anything like that, the inserts will all go to the delta store, accumulate, and then go to the Columnstore index. And when you query this table, you'll query both at once. So you'll get everything. If you query the Columnstore index and some of the data is in the compressed stuff and some is in the delta store, you'll get both automatically. Will the row store be a little slower? Sure, but that's no problem. Compared to the mountain of data that you have there, updating, compressing, and all that work will be much more work. So the delta store is how you manage small batches and single one-offs and things like that. All right, so how do your write operations work? Well, first of all, Insert operations happen one of two ways. A small insert under about 100,000 rows will go in the Delta store, and it will sit and accumulate until you eventually have enough rows. Then asynchronously SQL Server will say, we've got enough rows now, and it's not really a specific threshold. It really just depends on how SQL Server manages it and how you maintain it. It'll asynchronously move it into the compressed row groups, and then the Delta store will be emptied. In general, it's beneficial to insert large batches when possible. This goes against what you're kind of used to in transactional tables, where you may batch things to avoid big transaction and bloating the transaction log and locking your table. So inserting millions of rows at a time into a Columnstore index is not a big deal. In fact, if you're inserting tons of data and you batched it in 2 to the 20th rows at a time, that's kind of the optimal size because it's the size of a row group. So insert operations will go to the Delta store or the compressed index. Either way, though, they're pretty quick. Next, delete operations. Here's a secret. Not a huge secret, but if you've never really used these before, that's a secret. Data is not deleted from Columnstore indexes. The data is soft deleted. And so we'll demonstrate that soon in that you'll have a flag in there in your Columnstore index. So when you delete a row, the row stays there. It doesn't go anywhere. It's wasting space. And it's just flagged as is deleted one, basically. So there's delete bitmap, which is a B tree structure that lays on top of your Columnstore index, and that manages the rows that are deleted and tells SQL Server which rows to ignore or not ignore. So when you query your table, if there's deleted rows, it's gonna have to merge that data and say, okay, those 10 rows, don't include them, done. And so frequent deletes over time will cause fragmentation because you'll have more and more of these kind of ghost rows that are soft deleted, they're there, but they're not real and you don't use them. So deletes against Columnstore index are not slow, not necessarily bad, but they will cause fragmentation that you may eventually have to deal with in the future. So let's demo delete operations and how they look. So I've shown you kind of the metadata behind the scenes on Columnstore indexes. So we can view a before and after here. So here's a before. Here's my row groups. I can see I have 27 row groups, and there is a deleted rows column. It's 0 across the board. Let's say I jump in and say, delete 100 rows. So I go in, delete some rows. They're deleted. Now, they didn't actually delete. I just had a bunch of metadata get updated. Let's say I run the same query again, and I check the metadata. You'll notice that now I have some deleted rows here. And so my data has not changed in size, but there's now some delete bitmap activity here showing that these 3 row groups have some deleted rows in them corresponding to what data I just deleted. And so they're soft deleted. It's an important thing to keep in mind is that the data is not really deleted, it's soft deleted. How about updates? Updates are delete followed by an insert. We know that, but because this is a transactional universe, it requires writing to a delete bitmap and the Delta store simultaneously, which ends up being slow. This is not very well documented. On a small Columnstore index or on infrequent operations, you may not notice the latency, but against a very, very large Columnstore index, you may notice updates will perform very poorly. So a general best practice is don't issue updates against Columnstore indexes. Do everything you can to avoid them. Use inserts and deletes instead, avoid updating, use temp tables, whatever it takes, but do not update. And I'll talk about this a little bit more later on as well. But in general, update operations are worth avoiding. Hi.
Hey Ed. So Simon asks, with SQL Server 2016, you can truncate individual partitions. Is there a similar way to truncate / drop individual row groups? If I know that all rows of a particular row group need to go, it'd be great to be able to truncate instead of delete. What's your take on that?
Unless they're all isolated in their own partition, because you can do like partition operations you normally, you can operate on partitions in a Columnstore index just like you would in a standard table. So if you have the ability to do it here, a partition is full of data you don't need anymore, you can drop the partition. Can you get rid of a row group? Not exactly, but if every row in a row group is deleted and the rows deleted is, all the rows in the row group, and you run index maintenance on it, it will get rid of the row group for you. So that will happen in the background for you. Alternatively, if the row group is fully deleted, it will get ignored. So there's really no big deal either way, but that will get taken care of for you.
Thank you.
Cool.
We have also Michael. He says, I have a 16 billion row table in DWH on SQL 2014. I just inherited using traditional indexing strategies. Columnstore are updatable in 2014, including being able to use partitioning.
Yes, they're updatable. I would definitely use partitioning. Do issue writes against your Columnstore index, but avoid updates. I know we call them updatable, but updatable means insert, delete, and update. I would definitely isolate to inserts and deletes and avoid updates at all costs if you can.
Awesome, thank you. And before we move forward, this is the very last one related to this topic. How do you implement privacy regulations in a database where rows are not actually deleted?
So you can't view the data directly unless you like start DBCC paging it. But the answer would be index maintenance. When you run a reorg on a table with deleted data, Columnstore index with deleted rows, it will get cleared out for you. And so the answer, strangely enough, to how do you ensure the data is hard deleted and gone and nobody can go in there and sneak around and find it, would be index maintenance, which we'll talk about shortly. Not what you expect to hear, but it's the answer.
Thanks, Ed. Back to you.
Cool. All right, so I'll do a quick demo and update operations. I won't get into the latency issue. Just trust me, they're generally gonna get slow as we get bigger and bigger. I worked in Columnstore index with billions of rows. If you issue updates against billions of rows on many, many rows, you'll find that it will not run the way you want it to run. And in some cases, it can run so slowly it would actually harm your server performance. So avoiding updates is not a bad idea. So here's our before. We can see here's our Columnstore index. There are deleted rows from earlier, and then a whole bunch of goose eggs otherwise. Let's say we now update a bunch of rows. I run the update, and it was fast, but note it wasn't instantaneous. I updated my rows, done. Let's view the metadata again. We can now see some new things happened here. We can see we have some new rows that went in. There's an open row group at the end that's open. It can take more rows. There's 5 rows that I inserted. We can now also notice there's some more deletes back here too. These 5 rows here that are in the Delta store are the 5 rows that were deleted with reference to the update I just made. So the delete and the update I just ran in total resulted in a whole bunch of gackety-gook against our, for lack of a better term, against our Columnstore index. And you can see it's starting to become fragmented as we begin making changes to it over time. So in general, updates are sincerely worth avoiding against Columnstore indexes. So now for some best practices. This is where we got to fine tune and make our work better. So first off, I alluded to this earlier, data order is very, very important in a Columnstore index because by default, order is not defined. This isn't like a cluster index in a regular table where you pick some columns and it orders it all for you in the background magically. Here, there's no magic like that. If I insert a billion rows in a table and I don't have an order by, I don't do it in order, I do nothing, your data just goes in the table. And that's it. And even the order by won't guarantee order. So what's going to end up happening if data is all mixed up, it's in your Columnstore index, and you can't do row group elimination without order. So row group elimination relies on order. If you want it to occur, you've got to have an ordered table, and typically you're going to order by time. Time, as I mentioned, we often filter by in the world of analytics. We'll do monthly, quarterly, yearly, daily, whatever, week over week, month over month. But usually we're filtering over time, we're ordering, grouping by time. So technically, I have asterisks here, data order isn't necessary. If you have some magic way to separate out and make sure every row group has a unique or a limited set of values for the thing you care about filtering by, it'll also work, but typically data order is the easiest way to achieve that. So let's demonstrate it because this actually is very interesting. So we can take a look at our metadata again from earlier. Here's our row group metadata for the order date key column for these segments within this one, for the Columnstore index, in this one column, here are all the segments. What we note is that the min data ID and max data ID, this is either going to be the value in the table or a lookup if it happens to not be a numeric column, like a number, like an integer. So as a result, the min and max ID here are the same for all of them. What this tells me is that my date range is smattered across the Columnstore index across all the row groups. What this means is my data is not ordered. So we can now look a little more detail at the stats IO for this and say, all right, give me a quick sum for this past month. I get my sum. I look at my statistics IO readout, and I notice that, it did a bunch of reads. It took a lot of reads, like 17,000 reads. They were fast because it's a Columnstore index, it's highly compressed, but it took a lot of reads. And the key thing here to look at is segment reads. This here tells you how many segments did you read and how many segments did you skip. And this is using the metadata we talked about earlier. So because I have no ordering in this Columnstore index, I had to read all of them. It was still fast, but as your Columnstore index gets bigger and bigger and bigger, and we're talking billions and billions of rows, this won't be so fast anymore. And it will put pressure on your buffer cache as well. So I made another table. This one's the ordered version. Notice no index. I put on a standard cluster index. There's other ways to do this, by the way. You can insert the data date by date by date in order. I have existing data here, so I'm going to do it this way. So I put a clustered index on here. I insert my mountain of data, and then I do a creation of the Columnstore index, and I do drop existing. So you can see I'm dropping that existing Columnstore, the rowstore index, and plopping this on top of it. So basically, I created a table, I threw data in, it's all ordered the way I want it, and then I did a lift and shift of the indexes. So now the data is ordered by date, because my clustered index was on date. So now, if I run my same query from earlier, I note that I read one segment and skipped 22. That's a big deal. So now using the metadata stored in line with my segments, I was able to skip 22 of 23 segments. Now imagine this is a bigger table that had years of data or more columns I was seeking. Skipping segments gets huge fast. This makes a big, big difference in performance as your data gets bigger and bigger and bigger, because realistically, I may have 23 million rows here, and 23 million rows may sound a little big, but in the grand scheme of this kind of data, it's tiny. And when we talk big data, we're talking billions or trillions of rows. Now, even better, we can see the ordering here. We can note that the min data, max data now kind of goes in order. You can see that these kind of sequence and cycle through each other and go naturally through. So if I ever want a value for a date, the most I'm ever going to read is 1 or 2 segments, because it's fully ordered now, and the data kind of evenly spreads across. Cool. Next, a few people have mentioned partitioning. Partitioning is also awesome for a large Columnstore index, because again, as your data gets bigger and bigger and bigger and bigger, you may not need it all. And the old data never changes anymore. And so for maintenance purposes and other such operations, you can benefit from having partitioning and reading less segments. A Columnstore index that is big, that goes over many, many years, is a perfect candidate for partitioning, especially if it's well ordered. It'll further reduce reads, even more than before, and it'll extend row group elimination. You will see that we're going to read less segments, and we're going to consider less segments once we have partitioning in place. And as a bonus for partitioning, if you have maintenance operations you do, like backups or index maintenance or so on and so forth, you can do it partition by partition and not the whole blasted table. So this is huge. So, as is our tradition now, let's create another table. Let's first of all add in file groups. And I've done all this already because we don't have time for that right now. I added some file groups to our database. I added some files that will contain the data for our Columnstore index or anything else we have out there. A partition function that operates over years, and then a partition scheme that operates and maps those years into our partition groups and files created above. Cool. Now I make a brand new table, partitioned. I'm not very creative, sorry. And I make that on the partition scheme we just created. And then I run through the same rigmarole as before. I create a cluster index. I insert all of our data. And then I drop the cluster index and replace it with the Columnstore index. So really the only thing that changed here was this is now a partition table. Let's run our same query as earlier and get our result and check out the I/O. First off, note that the reads are way less. We're talking 25 reads instead of thousands or tens of thousands that we had earlier. And notice we read one segment and skipped 2. So we've now reduced the amount of metadata and the amount of segments that have to be dealt with by SQL Server significantly. And it may not seem huge here because the numbers aren't that big, but when your table is mountainous, being able to skip thousands or millions of segments will make a huge difference in performance. So we've gone from 23 segments, read 23, to 23, read 1, to 3, read 1. That's pretty awesome for performance sake. We can do a little more though. This is not as much a performance optimization as a space optimization and a resource optimization. Sorry, let's continue. We'll get to that in a sec, actually. I want to talk about this first. This is actually even better. I'll jump to the demo in a moment. We mentioned this before, avoid updates. I mentioned it here again only because it's a huge deal. It will be slow, it will be problematic, and it will make life a little bit difficult. So just avoid them. I've mentioned it 4 times. I don't repeat myself for no reason. It's a good thing to keep in mind. Another best practice, this is now probably a natural thing now that we've talked about it, but query fewer columns. Because Columnstore indexes are built for OLAP queries that operate over less columns and more rows, every column you don't include in your query means less segments being read. They're skipped via segment elimination. A select star query will destroy segment elimination. If you have 100 columns, you want to eliminate as many as you can. So it's almost a common sense best practice, but query fewer columns. And here's another cool one, archive compression. This is kind of what I was about to jump into a second ago, but it's worth finishing up everything else first. Archive compression is like Columnstore compression on steroids. It's even better. It has a higher compression ratio, but it costs more computing resources to read and write the data. Not a lot more, but it does cost more. But it reduces your storage and your memory footprint. So if you're reading this data and you're using it, it'll take up less storage on your storage, wherever it is, disk, whatever, and it'll take up less memory until you read it. So what is this good for? This is good for scenarios we don't read the data very often, cold, warm storage kind of deals, old data you don't touch much anymore, or scenarios where the time, the duration, the performance of your query isn't that important, like some report that runs after hours that goes back and grabs some old data and does some stuff with it. If you don't care about it, saving space could be important. And if your data is big, it could be a lot of space. So archive compression provides additional compression on top of what we already have at the cost of the computing resources necessary to write it mainly and to read it a little bit. All right, I like making tables. So we make one more table here. This is the archive compression Columnstore index table. Same deal as before. Everything's exactly the same, except when I get down to here, I use data compression equals Columnstore archive. Everything else is the same. So let's go back. And now that this table is created and populated with data, let's compare the storage footprint of all the tables that we've viewed so far. And keep in mind, the storage footprint isn't just storage, which everyone kind of thinks is cheap and easy. Your storage footprint is storage, it's memory, it's potentially CPU to operate in all that data. It could be network bandwidth of transmitting that data. So storage isn't trivial. It means a lot of things. Let's compare now. So our original table that had data in it from earlier is 5 gigs. That's our OLTP table with an index on date. I do have one additional table I introduced a little later that's a covering index. It's a little bigger. So these are transactional tables. There's how big they are. When I just used the Columnstore index, no optimization, no best practice, just a Columnstore index, it brought it down to about a 15th of the size. We saw that earlier. Now let's say we order the data. All we do is just order the data instead of having a smattering of data across partitions and row groups. That shrunk the data by over an additional 2/3 from what it was before. So we went from 5 gigs to 340 megabytes down to 100 megabytes. So simply ordering the data cut the data down to 30% of the original size. And then the archive compression drops down another 25% on top of that. So we went conceivably from 5 gigs to 75 megs. That's dramatic, and this is not unusual. This is not strange. This is not out of the ordinary, like Ed went in and played with the data and made it all special. This is real. This is real kind of data, and it shrank a lot. So the impact of compression in a Columnstore index is not trivial. This is huge. This is a big deal, and it makes a giant difference in performance overall. And I'll tell you, the Columnstore archive compression is going to be way faster than any OLTP alternatives you have. Even though it's a little slower than regular compression in the Columnstore world, it's still way faster than OLTP. All right. Common question people ask about Columnstore indexes: how do I maintain them? What do I do to keep them working well? What do I do to prevent them from getting fragmented, whatever fragmentation is? And in general, a Columnstore index will only get fragmented through deletes and updates and unordered inserts. So if you delete from a table, a Columnstore index, it will become fragmented because now you have soft deleted data in there. And you could run a reorg and get rid of deleted rows, but now you still have sort of wasted space because your row group is a little smaller than it could be. So over time, if that happens a lot, you're going to have lots and lots and lots of row groups, but they're all kind of small. And so you're reading more row groups to get your data, and that'll be a little slower. Updates, by definition, will make things fragmented because you're going back to your old data and changing things. And so when you change things, now you have your old deleted row, and you have a new row inserted in the end. That new row inserted in the end may not be ordered. So if you ordered by date, for example, and you go and update a bunch of rows from 5 years ago, those new versions of the rows will now be on the end of your Columnstore index alongside your new data. And so your data is not ordered anymore. And that's fragmented. And I got to read more row groups to get what you want. And undersized row groups, not a huge deal, but over time, if you delete a lot of rows, or you may eventually end up with a lot of undersized row groups, that can make things a smidgen slower. And then ultimately, Delta Store can create a little bit of latency as well. Not a lot, but Delta Store is slower to read from than a a column store index. So if maximum speed is what you want, you can use index maintenance to kind of clear out the delta store and push it out of the column store index. Again, it takes time, but that's okay. So what are our options here? Before I jump into that, I see we have a question. What's up?
Yeah, we have a couple questions, but I'm gonna just focus on the main ones that were related to the topic here. Keith is asking, what could be an indication when row estimates versus actuals are different in huge amounts in a column store index scan?
I missed that. Can you repeat that again, please?
What could be an indication when row estimates versus actuals are different in huge amounts in a column store index scan?
It's a good question. Typically, the only reason I've seen estimates get off in column store index is you have a lot of segments with a lot of segments that are very undersized and fragmented. That can result in stats being a little bit off because SQL Server knows the min and max IDs on each segment, and it knows the row counts, but it may not know how many rows match the filter criteria inside of there. And so the more segments you have to scan, potentially, the more the stats can get not, and there's no statistics like there are in a real table. It's not the same kind of deal, but the row estimates may get off the more you have that. And the delta store, same idea. So the more rows in the delta store, which is controlled, and the more fragmentation can lead towards potentially estimates being off.
And is there a difference between a reorg and rebuild on column store indexes?
Yes, there is. If there's no more questions, I'll jump right into it, or I'll just kind of answer that right now.
You can go ahead and jump into it, Ed.
Sure. So the difference between reorg and rebuild is here right now. I love it. So two choices like other indexes. How do you maintain it? A reorg is an online process. So you can run it while the index is in use and it won't cause any havoc. Basically, the main purpose of a reorg is you can process the delta store if you want, get all data out of the delta store and force it into the compressed column store structures. You can also remove deleted rows as well. And so some people, when they want maximum speed, will run reorgs immediately after data load to kind of get everything compressed into the column store index. Some people don't. It honestly isn't a huge deal in terms of speed, but occasional reorgs are useful because they will get rid of deleted rows. If you do delete data, a reorg could be useful. If you never delete data, though, and you're only inserting data, the reorg probably is not important. You could probably do it once in a great while, or maybe never. I mean, unless you run into some kind of changes that are big, you may not need it. And a rebuild recreates the whole index. So that's going to be slow. It is online in 2019 and later, but it is slow. It takes time. You're rebuilding the whole thing. If you have a partition table, you can rebuild some partitions, not all of them. That might make your life a little bit easier because in most OLAP environments, you have your old data that's huge and never changes, and your new data that's smaller and does change. So as a result, you may be able to take advantage of partitioning to make it a little bit faster. In general, a rebuild isn't that important on a column store index. The only times you may really want to do it will be if you have a lot of updates and changes that occur due to some maintenance or release, or maybe you've finished up and your partition is all done. It's last year's data. You're not going to touch it ever again. Do one last rebuild. It's perfect, and you leave it alone. In general, though, index maintenance is not needed very often if your data is ordered and you maintain that order and you don't run updates or deletes very often. If that's the case, you can run maintenance periodically at your own leisure. Realistically, you're not going to notice the impact of fragmentation unless you do a lot of deletes and a lot of updates. All right. Are there any more questions, by the way, Eric, on reorgs, rebuilds, maintenance kind of stuff? Or are we kind of covered there?
There's a couple questions that I'll share with you the one top voted one. Any special considerations for non-cluster indexes and built over a clustered column store index?
Great question. Your timing is perfectly, by the way. I will just jump right ahead using that question. We can continue with Q&A in a sec.
Perfect.
So you can, another consideration in the column store was so for everything we've done as a clustered column store index, which is awesome for OLAP data. You can, of course, create a non-cluster index on a column store index or a non-clustered column store index on an OLTP table. These handle the edge cases where you kind of have mixed OLAP and OLTP. I'll cover this scenario first and talk about the alternative next. So a non-clustered column store provides some OLAP support to a transactional table. One nice thing about it is you can specify your column list. That's pretty cool. You don't have to say, give me the whole table. I can specify the column list and decide what columns do I need or not need. But there are downsides to this approach because you're mixing OLAP and OLTP. There's a good chance that index will get fragmented very fast because most transactional tables are the target of lots of inserts, updates, and deletes. And if data is getting mishmashed and written to constantly, row by row by row by row by row, that Columnstore index is going to have a very active delta store, and it's going to have a lot of deleted rows and delete bitmap activity going on. So in general, it may make your Columnstore index a little less efficient than it otherwise would be. And writing to that Columnstore index and maintaining it will be slower too, because you're hitting data constantly, and the Columnstore index kind of prefers a scenario where you write to it less often. So the optimal solution, which I know we can't all do, is separate OLAP and OLTP. But if you do use a non-clustered Columnstore index, and it is a viable use case, important to test your reads and writes. Make sure your writes don't slow down, and make sure your reads are fast enough. The alternative to this would be a non-clustered column store on an OLTP table. Sorry, a non-clustered transactional index on a clustered column store. Gets a little confusing here. That scenario provides some OLTP support on an OLAP table. What you will notice is that index will be big. A transactional index cannot be compressed as a binary tree the same way a column store is. Let's say you have a column store index that's 100 gigs, and you slap a binary tree classic non-clustered onto it, it could very well be bigger than the column store index, or a significant chunk of the size of it. But it will provide you the ability to do lookups and seeks that otherwise could be slow. What I would recommend to you is, before you put a non-clustered index onto a column store index, test out just running your OLTP queries against the column store index, because the compression and the ordering may provide so much benefit that even just scanning a whole row group may still be pretty fast. So I highly recommend testing OLTP queries against the column store first. And then if it's not fast enough, then put a non-clustered index on top of it. But test first, because you may be surprised at how amazingly fast a structure that compressed can return select star queries when you don't expect to be fast. So, non-clustered indexes. We can demo them really fast and how they work. So we can go back to our original table from the beginning of this demonstration, where we had an OLTP table, and say, I have an analytic query to run. I run it. It takes a while. I'm running it 23 million rows later. This takes a while because it's a transactional table. I'm asking for 1 month of data, but I'm scanning a giant index, and that takes a while. And I'm scanning, and I'm scanning, and I'm scanning, and I'm scanning. At this point, you're probably bored of waiting. I'm bored of waiting too. Hey, look, I got results. So at the clustered index scan against my, sorry, clustered a index scan on that index that I put in order date key. It took a lot of reads, 595,000 reads to return my little sum. We know a column store index is faster, but what about a covering index? Let's say I put a covering index. So here's a new table one last time. I love new tables. This is an OLTP table, same as earlier, clustered on the key. And then I insert my data, and I throw a covering index on there. The covering index has my date key and my quantity. So if that query I just ran is really, really important, then I could put a non-clustered covering index and cover that query nicely. And now if I run it, I get my results a lot faster than before. And I note that the reads were way lower. Now, the reads weren't trivial because it's still a transactional table, and I'm trying to run an analytic query against it. But 1.5K reads is way better than like 600,000 reads. So a covering index may be a good solution to on your transactional table. But again, I highly recommend testing with what you have first, and then add on as needed. Never assume add more indexes. Test first and only add the index if you think it's needed. And then once you add it, it improves performance significantly. All right. So that's the non-clustered column store indexes. Were there any more questions, Eric, about any of the topics so far before I continue? I know I'm going fast here, and fast is fun. We cover a lot this way. It's why we're recording everything. So you can go back later and put it on 0.5, and then I'll be normal again.
And I mean, and also the beauty is that, people can get in touch with you. I know that you're going to share your contact information. So if there's a couple of questions in here that are not addressed, and they'll definitely be able to reach out to you. So rest assured for all of those out there, and if your questions. I do have a quick question. Instead of a lot of updates, would it be faster to explicitly delete those rows and then insert, even though this is what it does when you issue an update?
Yes, 100% yes. That is the ideal way to manage an update against the column store index. And as a bonus, you generally get a lot more control over your queries that way too. A lot of ETL and load processes will tend to, pull some data from somewhere, do things with it, and then insert it. It's way easier to do the things first here than insert later. So yes, I would highly recommend, and you can performance test it, but I would highly recommend delete the data, insert the data, and don't update it. It'll generally be faster, and it gives you a little more control over how you handle your transaction.
What about this one? If a fact table has multiple dates, are there benefits from ordering the rows by all of the dates and not just the primary date?
Sure. So when you order data within your Columnstore index, I demonstrated a clustered index that orders by date. You could order your data by more than one column, and what will happen is you'll have your date first. So all your row groups will ultimately be organized by date, but then within that, you'll have an ordering by other columns. So perhaps after date will come some customer ID or account ID or something. And then when you suddenly query into that data, if there's many row groups for one date, if you have a very large table, you have many, many row groups for one date, maybe you'll have further row group elimination based on additional ordering. Very, very good question. And additionally, if you do have the ability, you may want a non-clustered index for an alternative date. There's no better way to do it. But typically the second ordering or a third ordering or fourth ordering can give you better performance. So highly recommend if you do naturally order data by multiple columns, then order the data by that when you put it into your Columnstore index as well.
All right, and then the last one, and then I'll let you continue. Would it be preferred to have a cluster row store index and just create a non-cluster column store index so that the data will be ordered?
It's a good question. My recommendation, if you have a transactional table that you have some analytic queries that are running against, and you want to manage it in the best way possible, start with a covering index first. Let's say you run a sum across two columns based on date. So you have some select, you filter on date, and you do a few sums over two columns. Try writing, if it's very, and let's say it's a very important query that you run all the time. It's very, very harsh on your system, and it really kills your PLE, it hurts your server, does all those bad things you want it to do. You could say, hey, let me try a covering index first, kind of like how I demoed a second ago. And then, is that good enough? Or is it not good enough? If it's not good enough, the column store might be the way to go. But keep in mind that when you mix OLTP and OLAP, you're going to find that the performance of the non-primary method will be slower. If you put transactional on top of analytic, you'll find the transactional is kind of slower and less efficient. If you put analytic on transactional, you'll find the analytic is a little slower and less efficient as well. So I highly recommend testing a covering index first. If it's not good enough, try the column store. But just keep in mind, when you write that column store index in a transactional table, if that's the sort of transactional table that's heavily transactional, like heavily, lots and lots of reads and writes and contention and waits and deadlocks and blocking, your column store index is going to be very expensive to update. So I recommend the covering index first, followed by the column store if not all else fails. But I highly also recommend test each scenario thoroughly on a production workload, a real workload, to make sure that you don't slow your writes down or make the rest of your world slower. Because if you have a table that's primarily transactional, you want to service transactional first more than anything else. And if you slow down your transactional heavily to make the analytic faster, that may not be the way to go. So there might be architectural solutions as well that involve creating reporting tables and other structures to manage it separately. But that's a different session on database design for a different day. Cool. Let's continue a little bit further before we wrap up for questions. So another thing people ask, which I think is awesome, is, hey, column store indexes are awesome. Memory optimized tables are awesome. Therefore, we should mix the two, right? And put column store indexes in memory. It turns out, just because you like pizza and just because you like chocolate and peanut butter does not mean you should combine them together into a tomato pizza with chocolate and peanut butter on top. Combining two good things does not always make a better thing. And I truly mean it here more than anything else. Memory optimized tables were built for transactional workloads. They are meant for highly contentious transactional workloads, locking, blocking, deadlocking, all that good stuff that makes those heavily hit tables dangerous in production. A memory optimized table can take your transactional workload and get rid of a lot of the contention and make it very, very fast. Column store indexes are optimized for analytic workloads that are not updating, deleting, inserting constantly, and that tend to grab tons of rows in a non-contentious environment. You'll find when you combine them that typically it will be slower, it'll take up more resources, it'll use more memory than you expected otherwise, and it just won't give you any benefit. Even non-durable, if you try to go that route for some reason, you'll find that it'll take up more memory than you would have otherwise been taken up had you scanned the whole column store index into the cache. So in general, I recommend not using this. If you have an amazing use case where this brought you great benefit, I'd love to hear about it. Email me, contact me. I'd love to hear about it because as of now, I've not heard of a use case for us that was very compelling. In general, people have done it and been sad afterwards. So I highly recommend avoiding it. But if you have a scenario that works, I'd love to hear about it because in general, this doesn't work very well. So mixing peanut butter and pizza, not always good unless maybe it's dessert pizza, in which case maybe it's kind of tasty. All right, some notes on performance here. This is important. A Columnstore index is awesome. A Columnstore index is not magic. Despite the fact that it makes your data access extremely fast for analytic workloads, it is not magic. Ultimately, you have to read segments into memory to use them. That includes the metadata. So if you want to benefit from row group elimination, you have to still read segments into memory and read the metadata first before you can eliminate the segments you don't need. So you won't decompress the data and use it, but you may still have to read it into memory. So the more you can benefit from segment elimination, row group elimination, and partition elimination, which helps that along, the better it will get. And so in general, reading segments still takes time. If you want to grab 10 columns for the past 10 years and read 10 billion rows, it may still take a little while because there's no magic. You're still ultimately having to read data, but if you follow all the best practices, it'll still behave pretty quickly and amaze you at how fast it is. Another note on memory is that having memory is very useful for this. Do not put this in a reporting server that has no memory, because if you have an active chunk of data in your Columnstore index that is reported on frequently, you do not want to be reading it from disk. Once those segments are in memory, row group elimination is lightning. Data access is amazingly fast. And so having your most commonly used data in memory is useful. Quick example, let's say you have a Columnstore index that is a terabyte in size, but of that terabyte, only 10 gigs are really used very often, maybe 5 gigs. Make sure you have an extra 10 gigs of RAM dedicated to this index, and all that reporting will be amazingly fast because most of what you use will stay in memory all the time. You don't have to have everything in memory all the time. You will notice a significant speed gain over having to read segments from storage into memory. So optimal performance ultimately requires ordered data, partitioned if giant. And then as you load your data, do it via inserts and minimize deletes and updates. And be sure to order the data on the way in by whatever columns you want to order by. Usually a time dimension, but it may be other columns as well. You can order by more than one column if you wish to. And then when you query segment elimination is possible. A random note is that partitioning column and partitioning a table, if the key is longer than a certain length, usually around like date time offset 3-ish, you'll find that you can't get partition elimination anymore, and therefore you won't benefit from segment elimination. So watch your data types that you order by and make sure the key isn't too long, because that may break your partition elimination potentially. And last but not least, just have enough memory available to service your Columnstore index, because again, it's not magic. And therefore you will need memory, you'll still need storage, you'll still need resources to process your Columnstore index, but that's compressed so much, it'll be pretty tiny and nimble to work with. An additional note, you can store this anywhere. Like a Columnstore index does not have to go on premises. It can go anywhere. It can go on managed instance. It can go on a different database provider. It can go on really any hardware and software you want. I just showed my premises, my local machine. You can put them anywhere. So to kind of wrap up before we jump to questions, allow giant analytic data sets to be processed fast. If you want your data in SQL Server and you want it nearby, you want to have full control over it for the sake of adding columns, removing columns, and doing all those sorts of things, having it in Columnstore index is a great way to do it. It'll be fast, it'll be nimble, it'll be easy to work with. And while you can't quite just set it and forget it and slap a Columnstore index on and call it a day, the way, the general queries and processes needed to maintain a well-ordered index isn't hard. And once your queries are written and once your processes work, then you can kind of set them and forget them, and life works and it's good. And the beauty of it is that if you make good use of the data order and partitioning, you can really scale indefinitely. I've seen Columnstore indexes that go into the trillions of rows, and they're still fast. So the scale on this is amazing, and you can fully take advantage of it while following best practices. So here's my thank you. I hand it back to Eric for about 10 minutes of QA, if any exists. And if not, I can chat about peanut butter pizza, I guess. I don't know, whatever works. I'll keep it on topic, I promise.
I think people would like to know about your Lego collection. They can see it on the back that I've seen some comments in there. So
Oh, I tried so hard to keep that out of view to like avoid the distraction. For the record,
remember,
there's a lot of Legos over here that you can't see right now. A lot of
the
Legos.
good news is that we do have quite a couple of questions, so we'll go through those 10 minutes for sure, and we'll then take off the Lego discussion for another day. A quick one, will the scripts for these demos be available to download?
Yes, they're already there. When you go to check out the sessions, you'll find the files there. If for any reason you have trouble getting anything or have questions about the SQL or the presentation that I have there, feel free to contact me. My info is right here.
Perfect. Awesome. Thank you. So I have a couple questions, like I mentioned. Michael, he says, sorry for the dumb question. I don't think that any questions are dumb, but he says, but can I have a cluster PK and a cluster Columnstore index? Only one cluster index per table, but does this apply here also to the cluster Columnstore?
Yes. So you choose clustered Columnstore or you choose clustered like rowstore. You can't have both, and you don't really want both. You want to pick one as your primary. And the way to choose would be, is my table primarily transactional in nature, or is it primarily analytic in nature? And if it's very, very mixed, you may find a benefit in having that wonderful architecture project of splitting the two, which everyone freaks out about that, but it's a great way to improve performance is take it, split it, put them here and here, and then life is good.
So I have a amendment from a previous question from Carl White. He says, let me rephrase an earlier question. Any special considerations for partitioning, switching off tables with cluster Columnstore indexes as opposed to insert, delete, and update?
You can do it. And if you think, if it's convenient, if you have old data that you want to remove for archival or deletion or removal to cold storage or whatever, you can totally swap partitions, change the partition functions and schemes. Partitioning on a Columnstore index behaves basically the way it behaves on a standard table, except it's a Columnstore index. But otherwise, all the fun things you do normally can be done here as well. There's no real limitation on your tips and tricks that you can do. So if you've seen presentations on partitioning, it basically all applies here.
Awesome, thank you. Question from Tom: how would you approach a data set where the most recent year or two are frequently restarted, but history is never touched?
So you have ancient history that's cold and set, and you have modern history that's very hit. And the answer would be probably partitioning, maybe every 6 months or a year. And you'll accept the fact that a lot of your data gets touched. I would definitely say once your data is in that non-touch period, do your final rebuild on it, clean it up, make it nice. But I would definitely recommend reorgs. If you're touching your data frequently, a reorg, after your data load or weekly or monthly will be very beneficial. And again, test to see what's best. The reorg is online, so an index reorg will not be very painful. I'd recommend that, and that'll get you most of the way there. If you do reorgs on your data pretty often, that'll help a lot. If you find that row group elimination goes away because the data gets really mixed up, you may find that a rebuild every so often will be useful. Other than that, though, having a year or two of used data is not a big deal, as long as you kind of maintain it with a little bit of maintenance on the side.
Awesome, thank you. Another question from Carl, and I think this goes back to about beginning of your presentation. We have run into one problem with partitioning Columnstore tables. After partitioning, switching, dropping the table from which the partitions were switched can hang for literally hours. Is there a known gotcha around this?
I have not experienced that. I would love to hear about that, though, because I've not experienced that personally and heard about it. It might be Columnstore related. It could be partitioning or hardware related or some other configuration. Feel free to email me. I'd be very interested in, seeing whatever you have, hearing about it more, because that'll be something good to learn about, maybe document.
Awesome, thank you. Let me just mark this one as answered. What version of SQL Server is available in a meaningful way? What are the advantages as you move up the versions of SQL Server?
So in general, great question. In general, 2012, you couldn't write them. And so they were limited in use beyond I create it, destroy it, or make side-by-sides. 2014 introduced writing, and then with each version after 2014, they got better and better. I generally consider 2016 to be great. Once you get to 2019, you'll notice each version adds a little bit more. Like you have batch processing, which makes it faster. That wasn't available early on. The online rebuilds are also nice as well. So you'll find that each version gives you a little bit more. I highly recommend actually going to Microsoft documentation and checking out the full list of changes, because the change list between versions of SQL Server for Columnstore indexes is not massive. It's like a few things per version, very easily consumable, not confusing. I don't want to go trying to memorize and spit it all out right now because I'm not certain of all the things. But definitely you gain with each version. And I highly recommend reading it over first. But I would say if you're on 2016 or 17, you're in pretty good shape to make great use of them. No problem.
Awesome.
Any more
Thank you.
questions out there?
Yes. Why not leave the regular column cluster index in place to ensure order upon inserts or updates?
So why not use the transactional index in addition to a cluster column store or instead of? I guess
I'm
I'll
not sure if
guesstimate
that's
here.
what Doug is trying to say here.
Okay, so when I use the clustered transactional index, that was really just a cheat sort of to get my data ordered before I put the column store on it. If you're creating a table from scratch, you have no data yet, you'll be inserting it in order over time and it'll be ordered. I wouldn't recommend mixing the two unless you have a very mixed workload, in which case you're gonna have other problems. But the cluster index was really just a demo of how to get your data ordered. If you have an existing billion rows or million rows, or whatever, how do I order it up front before I put my Columnstore index there and get going, to avoid the issue that I had initially where I said, here's my index, give me my query. Oh, I didn't eliminate any row groups. So the ordering helps you with row group elimination. Hopefully I answered that. If not, I'm sure I'll hear back from you later, which is no problem.
Thank you. We got a question from Kevin as well. Are there any gotchas in this material that may not be totally applicable in older versions of SQL Server than 2019?
I would say the biggest gotcha, honestly, is rebuild. The online rebuilds are big. If you want to rebuild it, don't do it in an older version unless you have a downtime of some sort. And the writable is probably the biggest one. In 2014, they made it so you can write column store indexes. That's probably the biggest gotcha. If you try to do it in 2012, you can't actually write data to the column store index. You're forced to drop it, recreate it, do a side-by-side, some trickery like that. And so it's not easy. So I highly recommend, but from 2014 on, the functionality gets better, but the overall functionality is pretty similar, I would say. And again, the version upgrade list from Microsoft will tell you the details. So if you have a specific use case of something that may not be common, you can check it and know very fast if it applies to you. Because again, the change list from version to version on Columnstore is not huge. It's a small list, very easily to see.
Okay, I got a good one here. Is there a way to reserve minimal allocation for the Columnstore buffer pool?
To reserve minimum, there's no way that I know of to reserve it for just the Columnstore row group specifically. But if the memory is available on the server and not being hogged by anything else, you can use it. I suppose you can get to the governor, the data governor way of like managing it potentially. I'm not sure if I want to go down that road. Really, just making sure you have enough memory is probably the key, I think, available to the server and the database is really what you're looking for. If it's in a world of competing data where everything's using up your cache, you may read it. But again, I would also check first before adding tons of RAM up front. Make sure your stuff is fast enough, because it's quite possible that even reading data from your storage to memory, it may be possible the segments are already so small that it's not really that time consuming. And if it's fast enough for you, fast enough for your users, then maybe you're fine as is.
Question from Jason. What is the impact of, and sorry for just reading the acronym DOP, on compression when creating a Columnstore index?
So we're talking about regular compression. It's not heavy. I would say the effort to compress in a Columnstore index is not much more significant than a normal kind of index operation that you do. If you page compress a table, it's not that bad because the compression is very effective. So you may think, wow, it must be really expensive compression, but it's also easy because you're column compressioning, and if you have a million values and they're all one, that compression is not hard. So the effort to regular Columnstore compress a table is not high. You'll find most of your system resources are consumed by the effort of creating an index or rebuilding it or inserting the data, and not the compression. If you archive compress, it'll cost a little more, not a lot more, but a little more for the additional savings. It may or may not be worth it for you depending on your overhead. You may not need it. Your performance gains from the archival compression won't be really that big of a deal, but you'll save some space, and that is useful.
Great presentation, and thank you. But this one last question,
Sure.
Corby, is that a rocket ship behind you?
Yes, that is a rocket ship behind me. The kids blast off in it quite often.
Love it. Just a quick note here, and I actually just went to check myself. There are some comments from the audience that says that the scripts are not available to download. It's only the presentation. So can they get this from you directly if they, get in touch with you, or
I
should
would
we?
say give me a day. I will find out. I uploaded everything to the portal. I will check and see what happened. If I can upload it now, I'll upload it. Otherwise, I'll mail it to pass. So my goal will be to get it onto the page as soon as possible. So check back in a day, and I'll put a tweet out just mentioning the fact that I get them there when I do, just in case. But they should have
Perfect.
been there, and if they're not there, something's wrong.
I'll check also with my colleagues at Pass HQ, see what could have happened, and if perhaps if you folks out there in the audience want to check back the session, that same pop-up window, you want to check in an hour to see if those have been uploaded now, that'll be great. If not, you have Ed's contact information there. So I think that we are all covered here. Great comments from the audience. Thank you so much. And yeah, great presentation. And again, I guess the Legos too, and the rocket.
Thank you very much. I appreciate the laughs. I always like that. Feel free to contact me if you have anything you want to share with me or look me up. Feel free. If you have any questions. And otherwise, I really appreciate everyone taking the time to be here today and ask some awesome questions. It's great. Thank you.
Thank you. And thank you, everyone for joining today, Alan, Ed, Charlene, everyone for Carl, everyone for your questions. I think this has been great discussion here. And Ed, thank you so much for your time and a great presentation. I'm sure a lot of people here are looking forward to see the replay because there was a lot to cover, a lot of great information for sure. But yeah, thank you so much, everyone. Don't forget to please fill out the surveys, the session evaluation that helps Ed and also Pass HQ, to improve. Aside from that, you could be eligible to win a $50 gift card. So please don't forget to do that. And we'll see you next time. Keep enjoying Pass Virtual Summit 2020. Thank you so much, everyone. Goodbye.
Thank you.